Hello everybody and welcome to the 15th lecture of MHM 420 780 MUA 782. We finished the last session by talking about the water vapor migration in buildings. We solved one example, but I would like to solve another example today as well to make it clear for all the students. And after that, we are going to start talking about transient mass diffusion. Okay, so it's question 14.76 of your textbook. The diffusion of water vapor through plaster boards and its condensation in the wall insulation in cold weather are a concern since they reduce the effectiveness of insulation. Consider a house that is maintained at 20 degrees and 60% relative humidity at a location where the atmospheric pressure 97 kilopascal inside of the wall is finished with 9.5 millimeter thick gypsum wall boards, taking the vapor pressure at the other side of the wall board to be 0, determine the maximum amount of water vapor that will diffuse through a section. So there are lots of information, there are lots of numbers, but now we need to see how we can use those kind of information. From the previous example, we know that when we are going to calculate something like a water vapor migration in a building, the same thing that is asking here, determine the maximum amount of water vapor that will diffuse in 24 hours. So we need to find first our total resistance, and after that it will be easy. So let's write down the correlation first. So m dot first, again the same, we need to find m dot and after that multiply m dot by the time frame or delta t, which in this case is 1 day. We can find what the question is asking us. So a 1 minus 2 divided by r v total, and we said that this is equal to a relative humidity on one side, saturation pressure of side 1, relative humidity of side 2, pressure, saturation at temperature 2, and r v total. Okay, so let's first start with this one. So phi 1 or relative humidity of 1 is 60%. How about the pressure? So at 20 degrees we go to table. What table was that? 14.6. Am I right? Please go and check it. I think it was 14.9 if I'm not mistaken. Go to table 14.9 and we read it, and the saturation pressure at 20 degrees will be equal to 2339 Pascal. How about the phi 2? Let's go back and see where is phi 2. Okay, 60% relative humidity. Okay, the relative humidity of the other side is 0. What else we have? Okay, that's it. A, we have A as well, 3 multiplied by 8 square meter. So our total, as we mentioned before, is equal to our wall plus our film but here we need to find permeability as well as permanence, because this film is 1 equal to permanence. The permanence of 9.5 millimeter thick gypsum wall board of 0.051 millimeter thickness polyethylene film are given from where? Table 14.10. So our total will be equal to M1 plus M2 is equal 1 divided by 286 multiplied by 10 minus 9 S M2 Pascal plus 1 divided by 9.1 minus 12 kilogram S M2 Pascal. Okay, so our total will be equal to 1.1 10 to the power of 11, and the unit is SM2 Pascal divided by clicker. If we put that, because we have all the information, so M dot V will be 24 square meter, 60% relative humidity to 2339 Pascal minus 0 divided by 1.1. We just like from here so Pascal divided by kg, and we have it 3.06 10 to the power of minus 7 kilogram per second. The total amount of moisture that flows through the wall during a 24 hours period, as we mentioned last session, 24 hours is M dot multiplied by 24 second, so basically it's 3.06 10 to the power of minus 7 kilogram per second multiplied by 24 multiplied by 3600 second, so it will be 0.0264 gram, which is equal to 26.4 gram. Okay, so this is the maximum amount of moisture that can migrate through the wall, since we assume that the vapor pressure on one side of the wall to be 0. Note that the vapor, so it's very important, because you remember the reason why we could solve this problem out is because the question is asking about the maximum amount of water vapor. When we can get the maximum amount of water vapor, we get the maximum amount of water vapor when our driving force is maximum. When our driving force is maximum, when this phi 2 is equal to 0. Okay, so the wording, if it was not written maximum and it was asking determine the amount of water vapor, we wouldn't be able to do it. Why? Because the relative humidity of the other side was not given. Okay, I think that's it, and let's start talking about the transient mass diffusion. I want just to start with first talking about one table that you're in your textbook. If you see in that table, it's again, as I mentioned previously, we are trying to find the similarities between heat transfer and mass transfer to make your life much easier. If you can see here, there are lots of things that they look very similar to each other. And for example, if you remember from transient heat conduction, so of course we were talking about the temperature. In mass diffusion we are talking about concentration, but different ways of expressing the concentration, mole base, mass base. In heat conduction we had alpha. In mass diffusion we have DAB, diffusion coefficient, theta. In heat conduction, theta. In mass diffusion, and all the rest. Okay, so if we assume that the transient mass diffusion is the same as, like the correlations and everything is the same as transient heat conduction, so we should have something like this. If you remember the solution of transient heat conduction in a semi-infinite solid with constant properties under various boundary conditions could be calculated by using error function. It's from transient heat conduction. So temperature basically is based on the temperature, but here is ERF, error function, alpha. If we want to translate it into mass, transient mass diffusion, so of course instead of T we need to use concentration, error function again, and instead of alpha we need to use diffusion coefficient. But of course we said that for concentration we have different ways of expressing concentration, and there are different ways of expressing it, mass base, molar base. But let's talk about, because in this case we knew that it's an initial temperature, surface temperature. What is this what is this CAI? Basically it's the initial concentration of species A at time equal to 0. CAS, it's the concentration at the inner side of the exposed surface of the medium. Yeah, so just like a little bit different in definition, but basically it's not very complicated. We are familiar with it, and it's very simple, just like those concentration differences, and after that you need to use the error function, and the only thing that you need is x, time, and diffusion coefficient. Okay, but let's solve one example. And no, but before solving one example, let's talk about another important concept in mass diffusion. It's the depth of diffusion. Let me show it here to you. Okay, depth of, let me just like make it smaller. Yeah, depth of diffusion. but depth of diffusion is at a given time basically, so we call it penetration depth. So here it's like depth of diffusion, but we call it depth of diffusion at a given time, and we call it penetration depth. It's an important concept in transient mass diffusion. As you can see in the picture, it is defined at the location x. It's location where the tangent to the concentration profile at the surface intercepts the Ca equal to Cai line. So if there is this line is basically is Ca is equal to Cai. When that intercepts the x, basically this will be the penetration depth. So it's not very complicated. You see that there is a correlation ready for it, and penetration depth doesn't have any basically connection to concentration. The only thing that you need to calculate it is pi constant. You know it. You need to know the time, and you need to know the diffusion coefficient. Okay, so it's independent of concentration, basically penetration depth. Now let's solve an example and see if we understand it correctly. A thick nickel wall is exposed to pure hydrogen gas. The temperature is given. On one side, the hydrogen concentration at the wall surface is constant. Determine the hydrogen concentration at the penetration depth in percentage of its concentration at the wall surface. Okay, looks complicated, but actually it's very simple. So what we need to do is first we need to find the penetration depth. After that, when we find the penetration depth, we need to use that x, or penetration depth, into the equation that we had here. Here you see x will be penetration depth. First we use that x and we calculate. The second time we use the whole x, and after that we calculate it again, and we see how percentage and differences between them. So let's do it and see if we can get it done. So we said that for transient mass diffusion, we have CaXT minus CAI CAS minus error function of 2DABT. We also said that we wanted first at x, which is equal to penetration depth, which we said that is equal to pi DABT. Okay, so we just put it there. So CAX and T minus CAI, CAS minus CAI will be equal to ERFC equal pi DABT divided by 2 radical DABT. So basically is error function of radical pi divided by 2 is error function of 0.8 0.862. We go to table 4.4, and after that we can read this error function, which is equal to 0.2101. Okay, so what does it mean 0.2101? Basically is what the question is asking. Determine the hydrogen concentration at the penetration depth in percentage of its concentration at the wall surface. So basically CaXT divided by CaS will be 0.2101, so basically is 21%. Okay, that's basically that's it. Is there? Okay, so we are done with this transient mass diffusion, and now we need to start with a very important topic of mass convection. We start and to talk about it, and we see if we can finish it or not, but we are not in a rush, so I'm going to explain everything, and after that we see if we can finish it in 1 hour. I think it's enough because we are trying to always make it as similar as possible to heat transfer, and we talked a lot about heat convection, or at least during the previous courses, and you learned a lot about heat convection. So far we told you that we talked about mass diffusion, and we said that the mass diffusion was the transfer of mass due to a concentration gradient. But today we are going to speak about mass convection. Mass convection, or convective mass transfer, basically is the transfer of mass between a surface and a moving fluid due to both mass diffusion and the bulk fluid motion. So if you remember from the heat convection as well, that the bulk fluid motion was playing a critical role there. It's the same as here. But how do you remember how was it that in convection heat transfer, how the fluid motion would play a critical role? So fluid motion increases heat transfer significantly. How? By removing the heated fluid near the surface and replacing it by the cooler fluid further away. So it's a concept that even it's old and even used in lots of heat conditioning system. How we can extend it to the mass transfer? So we can say that fluid motion enhances mass transfer by removing the high concentration fluid near the surface and replacing it by the lower concentration fluid further away. This analogy between convection heat transfer and mass convection is valid for forced or natural convection, as well as laminar or turbulent flow regimes, or internal or external flow. You remember correlations for convection heat transfer? Most of them were empirical or semi-empirical ones. Why? Because the nature of convection heat transfer was really complicated. To find the H, which was the convection heat transfer coefficient, we had lots of problems. So that's a reason. That was the reason why we had to use semi-empirical correlations to calculate Nusselt, and after that, based on the Nusselt, calculate the convection heat transfer coefficient. We are going to have the same problem here as well. So basically, it is convection mass transfer is complicated, and it's not very easy to find a analytical solution for it. But we are going to talk about it. We are going to talk about similarities between convection heat transfer and mass convection, when we can use the same correlation, when we cannot. So don't worry about it. Okay. You remember that for convection heat transfer, first we started to talk about velocity, temperature, boundary layer in extended flow horizontal plate. If you remember, we were talking about, like, if we have a plate, the water it goes, and after that talking about no sleep condition, we were talking about how we define the boundary condition, where the boundary ends, and that 99%. We can do the same and use the same concept, but of course we know that there is no sleep condition in mass convection, so always we are going to have rho AS here. It's not going to be 0, but this is exactly the same as convection heat transfer, 99%. What are rho AS and what is rho A infinity? So rho AS basically is density of species A at the surface, and rho A infinity is the density of species A at free stream. It is for external flow. How about internal flow? Because you know that in even heat transfer we had that external flow, internal flow. For internal flow, we have concentration entrance region where the concentration profile develops, which is similar to thermal entrance region in internal convection heat transfer. So we if we apply the same concept here, as you can see in the picture, the concentration boundary layer continues to develop in flow direction until it reaches the tube center and boundary layers merge. Okay, if you remember from the boundary layer, that distance from the tube inlet to the point where that emerging occur is called concentration entry length. We call it with LC, exactly the same as convection heat transfer, which is if you remember this concentration entry length, it's if we want to find a similar expression for it in convection heat transfer, it was thermal entry length, and the same as convection heat transfer, we can say that the region after this point is called fully developed region. So after when they emerge, the rest we can say that is fully developed. Do you remember the definition of the thermally fully developed region from convection heat transfer? If you can't remember, please go and check page 476 of your textbook. Thermally fully developed region is defined as a region that dimensionless temperature profile remains unchanged. So if we apply the same concept for mass convection, instead of temperature, we should speak about some dimensionless concentration. Am I right? Because that dimensionless concentration profile needs to stay unchanged. if you remember, for heat transfer, that dimensionless temperature or that dimensionless number was Prandtl number, okay, which was momentum diffusivity divided by thermal diffusivity. But if we want to do the same concept, there is another dimensionless number in mass convection. We call it Schmidt number. Schmidt number is basically momentum diffusivity divided by mass diffusivity instead of thermal diffusivity. So it's very easy to understand. So instead of alpha, which shows the thermal diffusivity, we just replace it with DAB, which is diffusivity coefficient. Okay. So let's start with the other with Prandtl number. So we talked it, and we talked about Schmidt as well. But to present the relative magnitude of heat and mass diffusion in the thermal and concentration boundary layers, Lewis defined another dimensionless number called the Lewis number, as you can see here, and is defined as thermal diffusivity divided by mass diffusivity. So Lewis number basically is a Schmidt number divided by Prandtl, or alpha, which is thermal diffusivity divided by mass diffusivity, which is the DAB, or diffusivity coefficient. Okay, now we need if you remember, here we are just like, what does it mean when sometimes, so if you remember from convection heat transfer, we were saying that what does it mean when Prandtl number is equal to 1? But how about when the Schmidt number is equal to 1? Schmidt number equal to 1, it clearly shows that the momentum diffusivity is equal to mass diffusivity. But what does it mean? Basically, Schmidt number equal to 1 indicates that momentum and mass transfer by diffusion are comparable, and the velocity and concentration boundary layers almost coincide with each other. Here we also need to talk about the relative thickness of velocity, thermal and concentration boundary layers in laminar flow. I'm sure you are familiar with this one, that the relative thickness of velocity boundary layer divided by thermal boundary layer, we said that is equal to Prandtl to the power of n, and for most application n was equal to 0.3334. If we want similarly to define the same thing, so we can say that the thickness of velocity boundary layer divided by thickness of concentration boundary layer for mass convection should be somehow related to a Schmidt number, because a Schmidt number is a dimensionless number that plays the same rule as Prandtl number in convection heat transfer. So a Schmidt number to the power of n, and n again is equal to 0.3334 for the majority of application. But of course, if we want to have the relative thickness of thermal boundary layer divided by concentration boundary layer, it's going to be proportional to Lewis number, and the n would be the same. These relations, these three, normally in general are not applicable to turbulent boundary layers, since turbulent mixing in this case may dominate the diffusion process. But don't worry about it, it's a little bit complicated and we are not going to go into detail about that turbulent mass convection. So now let's start. Now I think we have all the basics and we are just trying to see how they are close to each other. We know from the Newton law of cooling that for convection heat transfer it was very easy. Q dot of convection was one constant, which was the sorry, not a constant, it was just a coefficient, which we call it heat transfer coefficient, convection heat transfer coefficient, H. It's multiplied by A surface area divided by delta T. So the correlation was looking very simple. So you need to have just the temperature difference and surface area. The only problem was finding this convection heat transfer coefficient. So if we want to more or less apply the same concept, we can say that the mass m dot convection is equal to mass transfer coefficient multiplied by A multiplied by concentration difference. But of course there are different ways of showing it, and you can show it mole base, mass base difference. Okay, and here you see that it's just like showing the concentration profile. As we said, there is a difference because there is no slip condition, so we are going to have a slope here. And how we can find that slope? Through the Fick's law. And if we say that for that specific for y equal to 0, the Fick's law will be equal to mass convection, and we can find it. Okay. But let's just like think about different situation and how we are going to sort it out, because there are like lots of other things that needs to be taken into consideration, because some of the times there are very similar, but you can't just like all the time change it from mass the heat convection to mass convection. You need to understand the differences as well. All of you are familiar with log mean temperature difference in internal convection heat transfer, or in your heat exchanger section as well, that you passed during the MTV 410, if I'm not mistaken. We use it in heat transfer because log mean temperature difference was obtained by tracing the actual temperature profile along the tube, and it is an exact representation of the average temperature difference between fluid and the surface for internal heat convection. So for internal mass convection, we can define more or less the same thing. Instead of log mean temperature difference, we can define log mean concentration difference, as you can see here. And I think that's it. Now I think we can talk about another important dimensionless number in convection heat transfer, Nusselt number, and try to find a similar dimensionless number in mass convection. We just said that for the problem with convection heat transfer was H. So H was very difficult to find. That was a reason why we, by using some empirical correlations, first we wanted to find Nusselt number, and after that from Nusselt number, by having Nusselt number and K and D, we could find H. It's the same. So we for mass convection, the most important thing to find the H mass. It's very difficult for us to find it. To do it, so we are going to define another dimensional number called Sherwood number. Uses the same kind of logic. Critical length is the same. Convection heat transfer coefficient. Instead, we say that mass convection coefficient, and here instead of K, we use diffusion coefficient. Mass diffusivity coefficient, binary diffusivity coefficient, different wording. Both the Nusselt number and Sherwood numbers represent the effectiveness of heat or mass convection at the surface. Like for Sherwood number shows the effectiveness of mass convection at the surface, and Nusselt shows the effectiveness of heat transfer at the surface. But if you look at that K and D, basically they are representing a little bit of conduction and diffusion. Besides that, we have heat transfer Stanton number. We also have mass transfer Stanton number. You can see the correlation for heat transfer Stanton number. Stanton number is equal to Nusselt multiplied by 1 divided by Reynolds, that multiplied by Prandtl, but in mass transfer Stanton number is Sherwood multiplied by 1 divided by Reynolds multiplied by Schmidt. For Nusselt number was a function of Reynolds and Prandtl. If you remember, the majority of those correlations or semi-empirical correlation, they had like one constant Reynolds to the power of something multiplied by Prandtl to the power of something. We are expecting to see the similar trend. So the Sherwood number will be a function of Reynolds and Schmidt. So we are expecting that correlations for Sherwood number be constant, Reynolds to the power of something, Schmidt to the power of something. Okay. Now the question is, because when we talked about that for a given geometry, the average Nusselt number in forced convection is a function of Reynolds and Prandtl, and average Sherwood number in forced mass convection is a function of Reynolds and Schmidt. Now the question is, these functions are the same. yes or no, and what does it mean if we say that those functions are the same. It means that Sherwood number can be obtained from Nussel number correlations by just replacing the Prandtl number by Schmidt number. If we go to table, if I'm not mistaken, yes, here, but we are going to come back and explain it. But if you look at here for table 14.13, there are different scenarios. For example, forced convection over a flat plate. If the flow is laminar, the Reynolds boundary, there is a Nusselt. The only thing that we had to do to use the same correlation for convection mass transfer was first to change the Schmidt boundary. Besides that, just take the same correlation, change the Nusselt with Sherwood, Reynolds stays the same, the power of Reynolds stays the same, constant stays the same. Instead of Prandtl, we put Schmidt and the power stays the same. Turbulent, again the same, combine laminar and turbulent with difference. So you see those situations. But let's go back, and after that we are going to, I just wanted to show that equation too. For natural convection, mass transfer is the same as if we use the same kind of mentality, we can say that Sherwood number is a function of Grashof and Schmidt. If you remember, for natural convection heat transfer, Nusselt number was a function of Grashof and Prandtl. So of course with the same mentality we can say that for natural convection mass transfer, Sherwood will be function of Grashof and Schmidt. So table 14.12 shows an analogy between the quantities that appear in the formulation and solution of the heat convection and mass transfer. As we said, in heat convection we are dealing with temperature and temperature difference. In mass convection we are speaking about concentration difference, but there are different representation of concentration, mass base, molar base. H convection means convection heat transfer coefficient. Similarly, H mass represents mass convection coefficient. Delta thermal, delta concentration, Reynolds the same, Grashof in heat convection. We use that correlation to calculate Grashof for mass convection. There is another correlation that we need to use. Prandtl in heat convection, we said that it's similar to Schmidt number in mass convection, both dimensionless. We said that we have two Stanton number, Stanton for heat transfer, Stanton for mass transfer. H convection or convection heat transfer coefficient, and here is mass convection coefficient. We said that Nusselt is another dimensionless number that we use in heat transfer, convection heat transfer. Similarly, we use another dimensionless number in mass convection called Sherwood number. We said that for natural convection heat transfer, Nusselt natural convection heat transfer, Nusselt is a function of Grashof and Prandtl, and for force one is a function of Reynolds and Prandtl. Similarly, we can say that for forced mass convection, Sherwood number is a function of Reynolds and Schmidt, and for natural mass convection or convection mass transfer, Sherwood number is a function of Grashof and Schmidt. So now if we want to talk about the analogy between friction, heat transfer, and mass transfer coefficient. And after, when we talk about that, we are going to talk about the Reynolds analogy. Another concept that we need to speak about it in mass convection is friction. Look at this picture. For at y equal to 0, because of no slip condition, the convection at the surface is equal to diffusion. Okay, why? Because for heat convection or convection heat transfer, we had a no slip condition, and it was something like this. So it was basically 0. But for mass convection, it's not 0. So there is like a line that the convection at the surface is equal to diffusion. Okay, so here when we are speaking y is equal to 0, the mass convection at the surface is equal to diffusion. So we have these three conditions at the surface for friction, heat transfer, and mass transfer, and it's for external flow, so on the surface. For internal flow, we can rewrite them differently. So first, it's shown in this slide, but let's first focus on external flow. As you can see, for heat transfer, what does it mean when we are saying that at the surface, like the no slip condition, it's like the concentration at I just want to find this similar meaning between heat transfer terms and mass transfer. So when we are saying that the concentration at the surface is equal to diffusion, we know that the diffusion we can calculate it from Fick's law. Okay, so diffusion is equal to mass convection. Similarly, in heat transfer, we can say that conduction is equal to convection. Okay, so we can use more or less the same concept for internal flow. Wall friction, heat transfer Nusselt, and mass transfer Sherwood. All of them at y equal to 0. Okay, we are familiar with this concept. We are not going to spend more time on it. One of the very famous analogy, if you remember, we had two famous analogies in heat transfer. Once the first one was Reynolds analogy, and the second was Chilton-Kilburn analogy. So let's talk about the Reynolds analogy and see how we can extend it to mass convection, and after that we are going just like to talk about Chilton-Kilburn. For Reynolds analogy, Prandtl is equal to Schmidt is equal to 1, more or less. What does it mean? It means that nu is equal to alpha is equal to DAB, and again all that. So if you remember from here, so wall friction, heat transfer, and mass transfer are the same. These relations, as I told you previously, called as Reynolds Analogy, and it is for us to will help us a lot to determine seemingly unrelated friction factor, heat transfer, and mass transfer coefficient when one of them is known. So for example, when we are saying that Prandtl is equal to 1, or the situation is like you can follow the Reynolds analogy and I give you the friction factor, you can say that okay, it's Prandtl is equal to Schmidt and is equal to 1, and from that you can find the rest of the information that you need. But the second Chilton's second analogy that was very important for us was Chilton-Colburn analogy, and it's like a bit of extent of Reynolds analogy when it was like Prandtl is equal to 1 and Schmidt is equal to 1. We wanted to see how we can extend it. So Chilton and Colburn in 1934 suggested that most successful they were the ones who successfully could extend that range, and basically if Prandtl is between 0.6 and 60 and Schmidt number is between 0.6 and 3000, we can use this correlation to connect wall friction, heat transfer, and mass transfer. So basically, Stanton of heat transfer divided by Stanton mass is Schmidt divided by Prandtl to the power of 2 divided by 3. This, as is mentioned here, this relation is commonly used in air conditioning application. Another important consequences of Lewis number is equal to 1 is that wet bulb and adiabatic saturation temperature of moist air and are nearly identical. In turbulent flow, the Lewis relation can be used even when the Lewis number is not 1, since eddy mixing in turbulent flow overwhelmed any molecular diffusion and heat and mass are transported at the same rate. This Chilton-Colburn analogy is valid in laminar and turbulent flow over plane surface, but this is not always the case for internal flow or for flow over irregular geometries. Besides that, we should know that there are some limitations on using Chilton-Colburn analogy. I think basically that's it. There are some you can see that there are some limitations are in heat and mass convection analogy. We showed these similarities and correlations that they derived for convection mass transfer based on convection heat transfer by just changing Nussel to Sherwood and Prandtl to Schmidt. there are more with the different conditions, fully developed flow in smooth circular pipe, natural convection over surfaces, and you can see, but for natural convection we are not talking about Reynolds, it's Grashof and Prandtl, and for natural mass convection we are talking about Grashof and Schmidt. The other important issue that we are going to talk about today is the simultaneous heat and mass transfer. Many mass transfer processes encountered in practice, they occur isothermally, and thus we do not involve any heat transfer. But some engineering applications involve the vaporization of liquid and the diffusion of that vapor into the surrounding gas or atmosphere, what like drying of the clothes. Okay, it's one of the best example of it. Such processes require the transfer of the latent heat transfer of vaporization HFG to the liquid first in order to vaporize it, and then such problem involve simultaneous heat and mass transfer. To generalize, any mass transfer problem involving phase change like evaporation, condensation, melting must also involve heat transfer, and the solution of such problem needs to be analyzed by considering the simultaneous heat and mass transfer. It looks a little bit complicated or overwhelming when we are talking about simultaneous heat and mass transfer, but don't confuse. It's not as difficult as you might think. It's much easier. We are going to talk about it. There is like some information about the energy balance on a thin layer of liquid. At the surface, you see that the Q dot sensible transfer is first the latent heat transfer. We said first we need to get by latent heat transfer, and after that it will be simultaneous heat and mass transfer. Table 14.14 of your textbook shows various expression for evaporation rate of the liquid into the gas through an interface area A under various approximation. As you can see, it's like for evaporation rate in general, m dot is H mass A divided by rho Vs minus V rho V infinity. If it's ideal gas, there is another correlation you can use. If we use Chilton-Colburn analogy, by knowing that H heat is for heat is rho Cp H mass Lewis to the power of 2 divided by 3, we can use the same concept for evaporation rate. So those are like some correlations that makes our life much easier. If heat transfer from the water body to the surface as well as radiation from the surrounding is negligible, which is often is the case, then the heat loss by evaporation must equal the heat gained by convection, basically. Why? Because there is no radiation, and so convection, the heat which is lost by evaporation should be equal to heat that gained through the convection. So if we put Q dot convection is equal to m dot V HFG, and after that write it down based on the Chilton-Colburn analogy, so we can have this correlation. Okay, so in order just to better understand what's happening, it's better to solve one example to see how we can use those all those correlations that we were talking into the practice. So I think two examples would help us a lot. Let's first start with this example. Is example 14.143 of the textbook. Let me just create some free pages, and after that we can start solving it. Okay, the question is asking jugs made of porous clay were commonly used to cool water in the past. Now we can understand why. We are going to solve it. A small amount of water that leaks out keeps the outer surface of the jug wet at all time, and the hot and relatively dry air flowing over the jug cause this water to evaporate. Part of the latent heat of evaporation comes from the water in the jug, and the water is cooled as a result. If the environment conditions are 1 atmosphere, 30 centigrade and 35% relative humidity, determine the temperature of the water when steady conditions are reached. So basically what is asking us is TS, temperature of water. Okay, so let's start and see how we can solve it. What do you think? What should be the first step? So let's start with rearranging the Chilton-Colburn equation. So if you see it here, if we rearrange that one, we can find the correlation for T. So Ts basically, if we rearrange the Chilton-Colburn analogy, it's T infinity minus HFG Cp Lewis V divided by M S minus P V infinity divided by P pressure. Okay, so for T infinity, do we have it? Yes, we have it, 30 degrees. I just want to see what we have, and after that we are going to go and find the information that we don't have. So do we have this, basically the partial pressures? No, we need to find it. How about the total pressure? Let's go and check the equation and see if we have it. Yes, 1 atmosphere, so we have it, is equal to 101.3 kilopascal. We have this one, we have this one. How about these two? Yeah, we have it. It's not a deal, we can just read it from the table, or if you know it. So V is equal to 18 kilogram kilomole, M is equal to 29 kilogram kilomole. So we have these two as well. So we need to find HFG, we need to find Cp, we need to find Lewis number. Okay, so Lewis number, we know that is alpha divided by DAB. Let's go and check if alpha or DAB is given. No, I don't see any numbers here, so it's not given, so we need to calculate those two. So the problem is here that we have the dry air temperature, but we don't have the surface temperature to find the like a property of the mixture at the average temperature, because we need to say that T infinity plus T S divided by 2, there is like a temperature, and after that go and find it based on the temperature. But we also know that for sure Ts is smaller than T infinity, and for the purpose of property evaluation we can take Ts to be 20. Okay, so here is just a guess, but can you guess 31? No, that would be wrong. Can you guess 40? No. Why? That could be wrong. Why? Because Ts cannot be higher than T infinity or environmental temperature of environments. Okay, so we assume Ts is equal to 20. Why? Because we just need the temperature to be to calculate this, and after that go and read the property. So we read the property and at 25 degrees. But the property of what at 25? Water is clear. Water we read it at 20 degrees. Why? Because of the surface temperature. But dry air, we read it at the average temperature of the hot dry air and surface temperature, which is 25 degrees here. Okay. What information from water we need? HFG. So we go to the table and we read it. HFG is equal to 2454 kilojoule kilogram. The PV is equal to 2.34 kilopascal. For dry air at 25, we also read CP 1.007 kilojoule kilogram, and we also read from the table alpha is equal to 2.141 10 to the power of minus 5 per second. Also, mass diffusivity of water vapor in air at 25 degrees can be calculated from this equation 2.5. Correlation, you can also use the table as well. So you can use table 14.4 at 25. Okay, so now when we have both of them, so Louis is alpha DAB, so Louis will be 2.141 to the power of minus 5 divided by 2.5 minus 5, so the Louis is 0.8564. So the air at the surface, we know that is saturated, and because of that the vapor pressure at the surface can be calculated simply as like a saturation pressure of water at that surface temperature. So what is the surface temperature? We said that we assume that the surface temperature is 20. Okay, so if the surface temperature is 20, if we go to the table, we can find that what is the saturation pressure at 20 degrees, which was equal to 2.34 kilopascal. Okay. And this P sat basically is this one. Vapor at the surface. But how about the vapor at infinity? For vapor and infinity, say that P V and infinity is equal to phi P sat, but at infinity temperature. Do we have the phi? Yes, relative humidity 0.35. How about the P sat at 30 degrees? We can read it from the table, is 4.246 kilopascal. So we have this to be equal 1.486 kilopascal. So we have all the numbers that we need. So TS surface will be 30 minus 2454 joule kilogram divided by 1007 kilojoule kilogram Kelvin, or C are the same, 0.8564 2/3 multiplied by 18 kilogram per kilomole divided by 29 kilogram kilomole multiplied by 2.34 kilopascal minus 1.486 kilopascal divided by 101.3 kilopascal. This gives us 15.9 C. So you might say that, yeah, it doesn't make sense, you know, that first start with the surface temperature and after that find out that it's a little bit off. Yes, that's engineering work. Now what you need to do is the next TS will be 20 plus 15.9, because it's 16 divided by 2. So we repeat it for 18. We read the properties at 18 to see what TS we will find. This time the difference between the initial estimation and the one that we find from the correlation will be smaller. But in the exam, if you face with those kind of questions, don't worry. If you do just once, you will be fine. You don't need to do the second time. But always keep in mind that those temperatures cannot be any temperature that you think. They follow some kind of engineering rules. For example, in this case, we said that the surface temperature cannot be higher than the hot or hot dry air temperature. Okay, keep those limitations into your mind. So let's solve another example a little bit more complicated, and after that finish this this chapter. So let me just prepare some free pages to see if we can solve this this question as well. Okay. So it's question 14.148 of your textbook. One way of increasing heat transfer from the head on a hot summer day is to wet it. You've seen lots of athletes do it, especially during the time that they are running, you know, doing sports, just like put water in their head. This is especially effective in windy weather, as you may have noticed. Approximately the head as like just consider head as a 30 centimeter diameter sphere, because of course different people, they have different shape, and if we want to really consider the shape, we can solve it, because we can't calculate the surface area and all those stories. So we consider head as a sphere with diameter of 30 centimeter. Is it a good assumption? Is very good engineering assumption. And temperature 30 degrees with an emissivity of 0.95. Determine the total rate of heat loss from the head at ambient air conditioning condition of 1 atmosphere, 25 degrees, 30% relative humidity, and wind, the speed of wind, we have at 25 kilometers per hour. In two different conditions is asking us to determine the total rate of heat loss from the head. A, when the head is dry, and B, when the head is wet. And here we can see the differences between just heat transfer, mass transfer, and simultaneous heat and mass transfer. The serine take the environment around temperature to be 25 degrees. Okay, let's start. So basically what is saying that we have a sphere, D is 30 centimeter. We have air through it at 25 degrees, 1 atmosphere, relative humidity of 30%, and with a speed of 25 kilometers per hour. If it's wet, it's 30 degrees on this side, and we will have, and we need to find that one. Okay, so the air water vapor mixture is assumed to be dilute, and because of that we can use dry air property for the mixture. So property of air at the free stream temperature of 25 and 1 atmosphere. From table A15 we can find K, we can find is, I just write it down, what C Prandtl is equal to 0.7296. Need to find U as well. Also for the surface S, so will be at 30 degrees, not 25. So basically it will be equal to 1.872 multiplied by 10 minus 5 kilogram per second. The mass diffusivity of water vapor in air at the average temperature. We need to calculate that at average temperature. What is average temperature? So we have 25 plus 30 divided by 2 is 27.5. If we convert it to if we want to use equation 14.15, we also can use table as well. We know that the H2A air is equal to 1.87, 10 minus 8, sorry, minus 10 here, minus 10 T to the power of 2.072 divided by total P. Here temperature should be based on the Kelvin, so it will be 1.85, 10 to the power of minus 10, 300.5 Kelvin to the power of 2072 divided by 1 atmosphere. So what we are going to have, pressure needs to be based on atmosphere as well. It's a semi-empirical correlation. You can also use the table as well. You don't need to use this correlation, and the answer will be 2.55, 10 to the power of minus 5. Okay. Now it looks like that we have some of the information that we need. But we also need to find some of those saturation pressures, because later we will need them. So the saturation pressure of water at 25, saturation at 25, it's 3.169 kilopascal is from the table. And property of water at 30 degrees, water at 30 degrees, so we read HFG, it will be 2431 kilojoule kilogram, and PV is equal to 4.246 kilopascal. Okay, this one is from table A9. We also said that the air-water vapor mixture is assumed to be dilute, so we can use those. We can go to table A1 and read R air is equal to 0.287 kilopascal, 3 kilogram Kelvin, and R water can be read from the same table as well, 4615, same units. Just let me write it down. Just wanted to save time, but units are very important. Never ever do that, miss any units. Okay, now it looks like that we could gather all the information that we needed, so let's start analyzing it. When the head is dry, because it's saying that in two different conditions, so first we are assuming that the head is dry. Head is dry. Okay, so when the head is dry, heat transfer from the head is just by forced convection and radiation only. Okay, why forced convection? Because we have a wind and it's very strong. So how we are going to find like a radiation? Can I say that the radiation is going to be negligible? I don't know. First let's calculate it. If it's very small, after that we can say yes, it is negligible and we don't have to really consider it. But first let's calculate it if we have all the information. So Q radiation because even if you see here, the emissivity of head is given. So let's try to find it and see if radiation is important or not. So basically it will be epsilon s Stefan Boltzmann constant, T surface minus T environment, power of 4, but you know that this temperature needs to be in Kelvin, so 0.95 pi 0.3 to the power of 2 square meter, Stefan Boltzmann constant, and after that those two temperatures in Kelvin divided by 4 minus basically gives us, please calculate it at home, it will be 8.3 watt. Okay, in order to find Q dot of convection, forced convection, we know that Q dot of convection is HAS TS minus T infinity, and Q dot total when the head is dry will be Q dot radiation plus Q dot convection. Okay, so it looks simple. The radiation we calculated. For convection we have AS, we have TS, we have T infinity. The only thing that we don't need is H, which always, as I told you, is the most important thing and very difficult to find. So for finding H, we remember from the convection heat transfers that first you need Reynolds, you find the Reynolds. After finding Reynolds, you need to find the right correlation for Nusselt. When you find the right correlation, you calculate Nusselt, and after that you can find H by using H is equal to KD Nusselt. Okay, so first let's calculate the Reynolds, because we are saying that it is forced convection, but what range of Reynolds we are talking? So Reynolds is VD divided by nu. We know the speed, but of course it's kilometers per hour. We need to change it to meter per second, so 25 divided by 0.6 second. Diameter is 0.3 meter, and nu we just read from the table 1.562 10 to the power of minus 5 second. Reynolds is 133,380. It's a very big number. So now we need to go and find the right correlation for it, because now we have the Reynolds number and we need to find the right correlation for it. But in this case, what we were not talking about mass convection at all, because the head was not wet, so the head was dry in the section A. So for that one, we need to go back to the chapter which is related to convection heat transfer. So if we go to page 452, we can find the right correlation for it. Nusselt is equal to 2 plus 0.4 Reynolds to the power of 1 divided by 2 plus 0.06 Reynolds 2 divided by 3 Prandtl to the power of minus 4 mu infinity divided by mu s to the power of 1/4. So if we put all those values there, we will get 268. Nusselt will be 268. Okay. So what is mu s? So it was read. It should be read at 30 degrees and infinity. So of course 25 degrees. Okay, so now we have the Nusselt number. We have the Nusselt number from KD. This Nusselt number H will be equal to 22.8 watts. Okay, now let's calculate the Q dot convection. So Q dot convection will be HAS TS minus T infinity is equal to 22.8 watt to Kelvin pi 0.3 to the power of 2 M2 multiplied by 25K, so basically is 32.2 watt. So Q dot total dry will be Q dot convection plus Q dot radiation is equal to 32.2 watt plus 8.3 is equal to 40.5 watt. As you can see, the radiation could not be neglected. Okay, it is smaller than compared to the forced convection, but you can't neglect it. Okay, now when we are done with the section A, we didn't use any new knowledge of like a mass transfer. We just were focused on the very simple radiation because the we had a temperature difference, but we didn't know that if radiation can be neglected or not. So we decided to calculate it, and at the end we realized that it couldn't be neglected. And we had emissivity, so it was very easy to find the radiation. For convection, so we used the same strategy. First, finding the property, calculate the Reynolds from Reynolds calculation of the Reynolds. You can have an understanding of what kind of flow you are talking, if it's laminar, if it's turbulent. After that, you can go and find the right correlation for Nusselt. When you have the right correlation for Nusselt, you find the Nusselt. When you have a Nusselt, after that you can find H, which is convection heat transfer coefficient. When you have a heat transfer coefficient, you can calculate the Q dot of a convection, and Q dot total was Q dot a convection plus radiation. But now for the section B, we need to determine, as you can see, let's go and check it one more time. It's saying that they determine the total rate of heat loss when the head is wet. So now it's like when it's wet, so of course we are going to have, we are talking about mass convection as well. So the head is wet, there is an additional heat transfer mechanism by evaporation. So we can say that Q dot total will be Q dot convection plus Q dot radiation plus Q dot evaporation. Okay, so Q dot radiation, let's go and see if being like head being wet or dry will make any difference. Here epsilon as sigma t, temperatures are the same, Stefan Boltzmann constant is the same, surface area is the same. The question didn't say any difference between emissivity for wet or dry surface, so it's the same, so radiation heat transfer will stay the same. So we just write it down, 8.3 watt. How about the convection? If we go, convection will stay the same as well. So 32.2 watt. The only thing that we need here to find Q dot evaporation. Okay, so let's start with calculating a Schmidt number. Schmidt number is V DAB. We calculated DAB and we read the mu from the table. We could also read DAB from the table. So basically it's 1.562, 10 to the power of minus 5, second 2.55, 10 to the power of minus 5, second is equal to 0.613. Okay, now we have the Prandtl number, Schmidt number, which is similar to Prandtl number. We need to find Sherwood number. So Sherwood number, how we can find it is we can use the same correlation that we used for convection heat transfer, but we just need to change or replace Prandtl with Schmidt. So it will be 2 plus 0.4 Reynolds to the power of 1 divided by 2 plus 0.06 Reynolds to 3 Schmidt to the power of 0.4 infinity mu s 1 divided by 4. Okay, we have the Reynolds, everything is the same, just Schmidt has changed, so Sherwood number will be 250. When we have the Sherwood number, so we can calculate the H mass is Sherwood number DAB divided by L, so H mass will be equal to 0.0213 meter per second. Okay, so how we could find the Q dot evaporation? So if you remember, Q dot evaporation was M dot V HFG. So FFG we have it, M dot we need to find. So far what we have is H mass. If you remember, M dot V was H mass S rho V surface V infinity. Okay, so this one we have it, it's equal to 0.0213 AS. Again we have it, pi 0.3 to the power of 2. So the only thing that we need just to find these two. Okay, so treating the water vapor and air as ideal gases, the vapor densities at the water-air interface and far from the surface can be calculated like this. At the surface is like pressure at the surface RT. Far from the surface is the partial pressure divided by RTS. Those two R's here, it will be T infinity, R infinity, T infinity. Okay, so in both cases this R will be the water. Here the temperature, you know that the temperature in this case needs to be Kelvin, so 30 plus 270 3, here is 25, so 25 plus 273. R, we just read it from the table, so constant. So the only thing that we need to find now is the partial pressure at the surface and partial pressure of water at the surface. So the air at the water surface is saturated. Okay, so the pressure can be, so 30, we have 30 degrees, so saturation pressure P sat at 30 is equal to 4.246 kilopascal. But PV infinity is not exactly the same, so it's pi P sat at T infinity, which is 0.3 T infinity was T infinity was 25 multiplied by, this is S, surface surrounding. Thanks. From the table, P sat at 25 degrees is 3.169 kilopascal. So this one is equal to 0.9507 kilopascal. Okay. So on the surface there is no phi, so basically rho S will be equal to 0.0304 cubic meter, and rho P infinity is equal to 0.0069. If we put it into the correlation, m dot v will be equal to 0.001415, and q dot evaporation is equal to 344 watt. Q dot total will be 32.2 plus 8.2 watt plus 344 watt is equal to 385 watt. Just look at that, compare 344 by 8.2 or 32.2. The heat losses from the head can be increased by more than 9 times, in this case by just wetting the head and allowing the heat transfer by evaporation. So as you can see, the things that the people do, or you can see, or you might do it during the sport or when the weather is very hot, has a complex physics and behind it. So you are right. Okay, that was the end of this chapter. I'm going to upload the assignments as well, so the for this chapter, but just keep in mind that the assignments you don't need to hand in them very fast, because it will be test 2, but I would like to upload it as soon as possible in order to give you some opportunity to solve some examples and make yourself ready for the test. That's it for today, and enjoy the rest of your day. Bye bye.